We now have the common source amplifier using drain feedback, and we have to analyze it properly to see the effect of extra components in the circuit such as RG, and also we have to find the correct constraints on the capacitor values. Okay. So this is the circuit you have, and you can think of it as, let's say you are shown the circuit for the first time. You do know how to analyze circuits, including MOS transistor circuits, and you are shown this for the first time. What would you do? First you would check the operating point, the DC operating point. For that you have to open circuit all the capacitors and short circuit all the inductors. In fact, I would encourage you to do that for this afresh, although you know the answer. Then you can find the VGS, VDS and so on, see whether it's in saturation or triode region or whatever, and then calculate the small signal parameters of the transistor. Then put down the small signal picture of the amplifier and see how it behaves. Okay. Now I'm going to skip the operating point part, because if I open circuit C1 and C2, the source and load go away and we just have the drain feedback circuit, and we know that both VGS and VDS will be equal to each other, and they will be equal to the threshold voltage plus square root of 2 times the drain current divided by mu n Cox W by L. Okay. And now let's analyze the small signal incremental picture of this. As you know, anything that is fixed, such as a fixed voltage source, that is shorted to ground, so this will get shorted to ground. And here we have a fixed current source I0, and this becomes an open circuit because there is no increment in that. It becomes 0 in the small signal incremental picture. This is an open circuit. Okay. So the circuit we will have in the small signal incremental sense is this is the small signal model of the MOS transistor. And we have the output coupling capacitor C2 and RL. This is VGS, and this GM multiplies this VGS. Okay. I'll mark the terminals. Initially, especially when you don't have much experience yet, please be careful about drawing the small signal picture. In fact, the best thing is not to change anything, but start from the total circuit and replace only the MOS transistor with its small signal equivalent. Okay. And then redraw the circuit as you wish to do. Okay. Now we have these two capacitors, and we know that we want these capacitors to behave like short circuits. We will evaluate the constraints later, but for now we will assume that they satisfy whatever constraints they have to, and they do behave like short circuits for the desired signal frequencies. Okay. We'll later see what constraints are. So the circuit we have is really simple. We have Vs, Rs, GM, VGS, where this is VGS, RG, and the load resistance RL. By the way, in all of this analysis, we have omitted the small signal output conductance of the MOS transistor. But if you do want to include it, it's very easy. Okay. Here it appears in parallel with RL. Okay. In some other circuits, it may be different, but in all the circuits we have discussed so far, in the common source amplifier, it appears in parallel with RL. So if you want to know the results, including the small signal output conductance, all you have to do is to consider the parallel combination of RDS and RL instead of the load resistance RL alone. Okay. Now this is just regular linear circuit analysis, and we have only two nodes in the circuit. Okay, and let me call this voltage VO, that's the voltage across RL. Okay, I will write down the node equations. Usually I prefer to do things systematically. Okay, and I would recommend the same, especially in the early stages when you are still getting practice with circuits. Let me copy over this. Now I will write the equation at this node and the equation at that node. That is the total current flowing into that node. Current flowing in RS is Vs minus VGS by RS. By the way, this VGS is also measured with respect to ground because the source is grounded. Okay, so be careful about that. That may not be true in all circuits. Plus VO minus VGS by RG, which is the current flowing through RG. This is equal to 0. And at this node, at the output node, we can consider either currents flowing into the node or away from the node. Since GM is already flowing away, I will take all the currents going away, this way, that way, and GM VGS. The current flowing out here, that is GM VGS, plus the current flowing out in RG is VO minus VGS by RG, plus the current flowing out in RL is VO by RL, and all these things sum to 0. And we have to solve these two, the system of linear equations for VGS and VO. The output voltage is VO. Okay. Now please solve this for yourself. I am going to just write down the answer. I am not going to go through the steps of eliminating the variables and all this stuff. So if you do solve for it, you will find V0 by Vs to be minus GM RG RL minus RL. Okay, this is in the numerator, and in the denominator you will get GM RL RS plus RS plus RL plus RG. Okay, appears to be a somewhat complicated expression. Remember, for a common source amplifier, the very basic version of the common source amplifier without any extra components, what should be V0 by Vs? It should be minus GM RL. Now we have a somewhat different expression, but let's see what that means. First of all, why did we have this RG? We have this RG to provide DC feedback to the gate of the transistor. It's needed only for the DC picture. It's actually not there in the small signal incremental picture of the common source amplifier. So when a resistance is not there, meaning it's open circuited, its value is infinity. Okay, so even without doing anything else, you can guess that this RG has to be very large. Okay, because in the small signal picture it should be as good as not being there. Okay, now let's go back to this expression here, right? Let's see what happens. Now let's say RG is very large. Okay, so that means that we have RG in the denominator and we have a number of terms. One of them is RG itself and we have 3 other terms, and let's say that RG is much more than each of those other terms: GM, RL, RS, RS and RL. And similarly in the numerator, let's say that the term containing RG is much more than the others, that is GM, RG, RL is much more than RL. In this case, I can neglect all the other terms and retain only the terms containing RG. Okay, remember, even intuitively we know that RG has to be large, and now we are kind of taking an extreme case. It's very large. We have not quantified it yet, but it's very large and overwhelms all the other terms. So this can be neglected, this can be neglected, that can be neglected, and in the numerator that can be neglected. If we do that, this approximates to minus GM RG RL divided by RG, which is equal to minus GM RL. Okay, and it's exactly the same as the expression for the gain of a common source amplifier. So it does behave like a common source amplifier if RG is very large. How large should it be? It should satisfy these two constraints. But actually we see that if you satisfy one of them, others will be automatically satisfied. Okay. So first of all, we are looking at an amplifier. So the quantity GMRL itself can be expected to be much more than 1. Okay, it's definitely more than 1, it could be substantially more than 1. So it's very obvious that if RG is much more than this first term, it will be automatically more than that one and that one. Okay, because you have this GMRL multiplying that, right? So essentially the condition we need is for RG to be much greater than GMRL RS. Okay. Now the second condition says that GM/RG/RL must be much greater than RL, and RL is common to both sides. So it's really saying that GM/RG must be much greater than 1. Okay. And you can see that this is also automatically satisfied if RG is very large, because we expect the gain GMRL to be much more than 1, and RG is much more than RL from the first condition. So this will also be automatically satisfied. So essentially what you need is for RG to be much greater than GMRL RS. Okay. Now of course you can ask, what happens if the source is ideal, the signal source is ideal and RS is 0? Then this says that RG is much more than 0, which is true for any number RG. So in that case, if RS is very small, then satisfying the first one here, for instance, if RS is 0, satisfying the first one doesn't mean others are satisfied. In that case, basically RG has to be much more than RL. Okay. So RG has to be much more than GMRL RS or RL. Okay. So I just explained it with RS being 0. What you can do is solve for the gain V0 by Vs with RS specifically being 0. Okay. If we do that, for instance, we get, let me substitute that in here. If RS is 0, we'll have GM/RG/RL minus RL, and in the denominator we'll only have RL plus RG. So if RG is much more than RL, this goes away and this also goes away. Okay. So once this condition is satisfied, you will have the behavior of a common source amplifier, although there is a resistance between drain and gate. Okay. So that's the constraint on RG, and this is a very common situation in circuits. Okay. So you want the element to be significant for some picture, let's say DC or AC picture, and insignificant for the other one. And what you have are constraints. Remember, you don't get from this analysis RG should be equal to something. Okay. So RG has to be much more than something, and you have to choose something much larger than that. And just like I mentioned for the capacitor, you could choose, let's say, 10 times or 100 times more and be done with it. Okay.